I would like to show you a simple example calculation with the random sum generating functions in this video. Suppose you run a little store, and in your store you have a random number which I'm going to call y of customers per day, say, in a day, and of course this is a non-negative integer number, and let's suppose that customer I spends in your store xi pounds, which for simplicity I'm going to assume that it's a non-negative integer, but actually pretty much any conclusion we make in this example is true for any variables I really, xi, any variables xi. I'm going to assume that these are IID, that's important, and also independent of y, as we did for the last video. And if I calculate z to be the sum up to y of the xi, then this is going to be the total amount spent in your store. And assuming that the xi's are also non-negative integers, again the conclusion I make is true for pretty much any xi's, but let's assume they are non-negative integers. Then we know that pz of s is going to be py of px1 of s. Okay? What I'm aiming for today is to find the expectation and variance of this total amount. Find out from the generating function what is the mean and variance of the total amount spent in this store per day. Okay, so let me start with the expectation of z, and everybody hopefully remembers that if the means are finite, if the random variables are finite with probability 1, which we assume they are, without saying, I'm going to assume that these xi's have finite mean and variances, and in fact I'm going to put this down here straight away. So let's assume that the e of the xi, they are IID, so they all have the same mean, is mu and is finite. The xi are non-negative integer. The variance of the xi is sigma square, and again it's finite. Let's assume this. Okay? And because they are IID, it doesn't matter which index I take here. Alright? And so the expectation of z is the derivative of this generating function of z at s equals to 1. This we hopefully all remember from when we define the generating functions. And actually there is a way to get this in terms of the generating function of x1 and y. So all we need to do is differentiate this composite function. How do you differentiate a composite function? You differentiate the outer one, so p of y, and you leave what's inside, but then you multiply with the derivative of the inner function, and finally I need to plug everything at s equals to 1. Okay? Now at s equals to 1, I'm going to find at s equals to 1, if I plug s equals to 1 in there, then what I'm going to find is that I have p of x1 at 1, and x1 is a proper random variable, so p at 1 is just going to be 1. So when I plug in s equals to 1, then I get a 1 here. And of course when I plug in x equals to 1, then I get a 1 there. So let me proceed with this line as p prime of y at 1 times p prime of xi at 1 again. But then we remember that p prime of a non-integer random variable, non-negative integer random variable at 1 is just the mean of the random variable. So we end up with the mean of y for this first bit times the mean of the xi, which is mu, for the second bit. And so the expected amount the customers leave in your store is, of course, the expected number of customers times the expected amount each customer leaves there. And this is a special case of something called Wald's identity. And Wahl's identity is more general than this. For Wahl's identity, you don't actually need to assume independence here. You can relax this a little bit to be a stopping time, but let me not go into that now. But certainly it works for independence. But that's a simple way of proving this identity for independent random variables using the generating functions. The other thing I want to do is turn to the variance. And how can I do the variance? Well, remember that I don't do variances directly from generating functions. What I can easily access from generating functions is the second factorial moment, expectation of z times z minus 1. Because this is going to be the second derivative of the generating function at s equals to 1. This is again something which we covered before when introducing the generating function. So I already have my first derivative above. I need to differentiate this once more to get the second derivative, plug in s equals to 1, and that will give me a formula for the second factorial moment. So let's do that. What I see here is a product, and I need to differentiate the product first. So I'm going to start with differentiate the first factor, and that gives me a second derivative of py. But then again, it was a composite function to start with in this first factor. So I'm again going to have a first derivative of x, px, and I had another of that, so it's going to be the square of the first derivative together with the second factor. That's the first part of the derivative for the product. And then I'm going to have the second part when I write the first factor as it was and differentiate the second factor again. So that brings that into a second derivative. And finally, I have to plug s equals to 1 everywhere. Okay? Now, as before, I am going to have s equals to 1 plugged in here. S equals to 1 inside the generating function gives me 1 again. S equals to 1 plugged in there. It gives me 1 again. And so I end up with the second derivative of y at 1 times the square of the first derivative of x at 1 plus the first derivative of y at 1 times the second derivative of x at 1 again. And now I can plug in these things in terms of expectations or moments of x and y. The second derivative of the generating function at 1 again gives me this kind of factorial moment, e of y, y minus 1. This is multiplied by the expectation of xi, which actually I called mu, so I'm going to put here mu. Then I have the first derivative of y at 1, which is the mean of y. And that's multiplied with the second derivative of the xi, the generating function for xi, which is the mean of x minus 1. Okay, so this is how far I got with that. All right, now let me proceed here and just write this out a little bit before we do anything else. Let me write this out a little bit. And I'm going to write this as the second moment of y when I do this product here, minus the first moment of y, mean of y, times mu, plus the expectation of y, times, and so here what I'm going to have is expectation of x square, so that one I immediately write as variance plus square of second moment. Variance plus square of second moment. This is when I do, let me bring another color here. This is when I do, what's a nice color? Let's use this color here. When I do e of x square, that gives me these two terms. E of x squared, that gives me these two terms. And I also have a minus e of x which is a minus mu. So this is my formula for expectation of z, z minus 1. And now I need to do a variance out of this. So the variance of z is expectation of z, z minus 1. Oops, z times z minus 1. Well, that's not equal yet, because I have a second moment here, but in the variance I had a minus square of the first moment, whereas in here I had a minus first moment only, so I have to add that back. And then I can plug in everything from the previous lines. So e of z, z minus 1 gives me the line above. So it gives me e of y squared minus e of y multiplied with mu, then plus e of y times sigma square plus mu square minus mu. So far I wrote down the second factorial moment of z from the previous line. I just copied everything from the previous line. Then I have minus e of z squared. E of z was ey times mu. So I have a minus the square of ey and the square of mu for the square of ez. And then I have an ez, which again is ey and a mu. And now I have to collect everything together, and a couple of things will cancel. This guy here, e of y times mu with a minus cancels out with that with a plus. And then, mistake, of course, I had a square here which I forgot to bring over. So this one is squared, and that will give me a square on top of this mu here. And if I bring this forward, that will give me a square there. And if I bring this over, that's a square here, which means I cannot cancel out this term with this one. I can instead cancel out this term, minus e of y mu squared, with that one, plus e of y mu squared. And I am not cancelling with e of y mu. I have it back here. Okay, so now it should be fine. And what I want to do now is carefully collect the terms I need, but in fact before I do that I realized there is one more thing I can cancel with, and that's the e of y times mu. So I can cancel this minus e of y mu with this plus e of y mu. And so what I'm left with is a, let's collect the mu square terms here, the mu square terms here, e of y square times mu square and e of y whole thing squared. The difference is, of course, that y square is in the expectation here and it's out of the expectation there, times mu square. So this is this term and this term, and I have these people, just this term here, which is e of y sigma squared. That's all that's left. And actually here everybody recognizes the variance of y. So it's the variance of y times mu square plus e of y times sigma square. And that's the final formula for the variance of z. And now this is actually quite an interesting feature, quite an interesting phenomenon we see here. The spending of customers left in my store has a variance, has fluctuations, and those fluctuations are coming from two sources. There is a fluctuation of individual, that's what I want to point out first. There is a fluctuation of individual spending, sigma square, a variance of individual spending, and if I multiply with the expected number of customers, the individual variances, that's one component of my total variance for the sum per day. And there is another component, which is the variance in the number of customers. And if I multiply that with the mean square, the squared mean of how many customers, how much money they spend, that's mu square, that's the other source of my variance. So there are two sources, individual variances times expected number of customers, and variance in the number of customers times the square of the mean spending per customer, which is quite a nice formula.